Over to you, Pete.
Right, good morning, everybody. I'm Pete Brownlow, and the original plan was to run a DCC, Introduction to DCC workshop over the weekend. Obviously, we can't do that, so this is a little sample of some of the things we might have covered. What we'd normally do on the weekend is on a Saturday morning, we would do the presentation that I'm about to do for complete beginners, new to DCC. And then we'd move on to more workshop things, fitting decoders into locomotives, trying out programming them. Indeed, anybody wants to do on the course. So hopefully we'll be able to do that at some point in the future, and maybe see some of you in person when that happens. I've got a demonstration layout, and if you find in your gallery or your view the Pete Brackett's laptop picture, that's the camera that's behind me, and that's showing the layout a little bit more closely. It's running a sort of automatic sequence at the moment. I'm going to pause that in a moment. In fact, I'll pause that now, because otherwise the noise of the points changing and everything might override my presentation. When I'm doing any demonstration stuff, and if you do want to see the layout more closely, you can find that picture in your gallery, and the little 3 dots to the top right. If you click on that, there's an option to pin it, which pins that particular gallery picture to your bigger screen, so you can actually see the demonstration I'm doing. What I may also do is move back, because that's running off the laptop, that camera, so I might switch and talk into that one instead when I'm doing demonstrations of stuff, so that should then automatically come up in your speaker view as well. In the meantime, I'm just going to get the presentation ready here. And I think ideally my plan is to talk for an hour or so, and then have a break, coffee break or whatever, and then take questions. We'll see how it goes. The idea is to try, with so many of us, it's probably best to defer the questions to the end. But by all means, put them in the chat, and then we can work through the questions in the chat when we come to the questions section. I'm going to share my screen now, so you should be able to see my presentation. Right. So can everybody see that, my presentation?
Yes.
Yes, no, of course everybody's muted, but just give me a few thumbs up, so it'll be fine. Okay, so DCC, what's it all about? And as I said earlier, I'm assuming no previous knowledge, other than perhaps what a train is, and perhaps a little bit of awareness of how one might have controlled trains before DCC, and as indeed many people still do today. I'm getting bing bongs. Is that my computer, or?
I think people joining the meeting.
Is that all it is? Okay, no problem. Yeah. I wondered whether I was creating bing bongs, but obviously not. Good. So DCC, what's it all about? Let's have a look at that. So I'm going to talk about what actually the term digital means, because our lives are surrounded by the term digital. What that really means, and then how it applies to model railways. How's DCC different from the analog system that we might have been more familiar with? The pros and cons, warts and all, of DCC. What you need to do to convert to DCC if you're not using it already. Controlling trains with it, and controlling point signals, and the rest. And that's really the scope of what we'll get through. And there are lots of more other topics we can probably cover, maybe in the Q&A, but we would have covered in more detail on the residential course, which we hope to do in the future. So what's this term digital that's all around us? Because we're all using digital everything, everything from digital mobile phones to digital TV and all sorts of things. So what does that mean? Well, first of all, we need to think about what's the opposite to digital. Well, the opposite to digital is what we call analog control. And by that, what we mean is that the voltage we use is an analog of what we want to happen in terms of the English words. So hence, we tend to refer to it somewhat confusingly in model railway terminology as DC control, because we're using a DC voltage, which to my view is too similar to the term DCC and can cause confusion. Technically what it is, it's analog control, because the voltage we use is an analog. So, if we've got an old analog TV, none of them work that way anymore. But you'd have got more volts coming through onto the screen, and you'd get more colour or more brightness. With a train, maybe if you stick 3 volts up it, it'll go at a scale 30 miles an hour. It may not, but the voltage is an analogue of the actual speed the train will go, because you put the volts straight on the motor and it just responds. And as I said, not all trains will respond the same. And of course, any train that gets that voltage on the track will move with analog control. Hence the more complex analog layouts, DC layouts, will have lots of section switches, so you only send the voltage to the train you actually want to move. You have to isolate all the trains you don't want to move. And typically many sections on a complex layout. So the alternative, let's look at what we mean by digital. Well, first of all, digital refers to digits. And what is a digit? Well, I was careful which finger I chose, but effectively it's something that's there or something that isn't. So normally with the way we count, we may be teaching some people to suck eggs here, but we'll hopefully those of you who know all about this will persevere with me. I can tell by who's yawning, but so we have 10 fingers. So we can count to 10, and that's why we use 10 as our base. We count to 10, and then we add another digit. So 1, 0 means 10, because now, and then we count up again on our fingers. And that's how we count with base 10. But if we were to do that electronically to count, we'd have 10 different voltage levels to represent each digit. And if you get a voltage drop, you're going to get the wrong answer. So that's the why electronics doesn't really work that way. And also, if we've got other things like magnetic storage, DVDs, optical, all this sort of stuff, it's difficult to have 10 different levels when we're counting. So we introduced the concept of a binary digit, which is, think of the digital electronics as though it's only got one finger, hence my picture earlier. It's either there or it isn't, two states, a 0 or a 1. It could be in the old-fashioned days we had paper tape, which had a hole or didn't, magnetism on your hard disk, either there or it isn't, dents in your little on your DVD that are optical, it's either there or it isn't. Modern USB drives have an electronic state stored inside it, either there or it isn't. It could be inside an electronic circuit, it might be 0 volts for 0 and 5 volts for it's there. So you only ever have these two states, and that's why it's known as binary, because binary means two things. And so what we do is we count to 2, and then just like we add another digit when we get to 10, we add another digit when we get to 2. So 1, 0 actually means 2. Don't worry too much if this is going over your head, but because you don't have to understand this to understand DCC, it's really background. So we have this concept of binary. So 0, 1 is 1, just like it would be in a decimal, but 1, 0 is 2, 1, 1 is 3, and so on. 1, 0, 0 becomes 4. So we count in this binary way inside anything that's digital, and so on. And these are called binary digits, or a bit for short. So if you've heard the term bit is a binary digit, and hence the term digital, because it's actually binary digits. That's where the terminology comes from. So we already discussed how if we're going to send a speed command to a loco with an analog layout, we just stick the voltage down for how fast we want it to go. Binary is different. What we need to do is we need to send electronically the value of these ones and noughts, the bits. And what you can do, and this tends to happen inside a computer, is you can have one wire for each bit and send them all together in what they call in parallel. And we have a terminology where if you get bits grouped into 8s, they're called a byte. And half a byte, strangely enough, is called a nibble, 4 bits. So, and you'll hear the terminology of 32-bit computers, 64-bit computers. What that means is how many wires are all paralleled up to send the information all in one go. So if you've got 64 wires, you can send the information twice as much as if you have to send fast as if you have to send it over 32 wires. Hence the insides of your PCs are way up at 32-bit, 64-bit. We don't have that inside model railway locos. So here's the concept. We might, if we want to send a byte at a time, we might have to have 8 wires, and you always have to have a 0 volt return, just as with an analog send a voltage down, you've got to have a return 0 volts. So that's how you would send data in parallel. But that's kind of difficult to get down to our locomotive on the track. So the other way we do it is we only have one wire, and we send each binary digit one after the other, and that's known as serial. Here we are. So we still need our earth return, and we have one wire, and we send all the information one after the other. Now that looks a bit like a pair of rails, doesn't it? And that's how we do it. So we're going to send our information down the track, one bit at a time, one after another, to build up the numbers, for example, of how fast we want the train to go and which train we want to work. So that's just a little introduction to the concept of what is digital. So in digital control, we actually send a binary number for what we want to happen. And this is in all things digital. So for TV, instead of sending a voltage for how bright it wants to do, we send a number in binary of how much of each color, or lots of numbers in fact, how much of each color, how bright it is, and so on. And then the electronics in the TV works out what to do with that. Same with the train. If we want it to go at 30 miles an hour, we might send it the number 30 in binary as a whole lot of bits, one after the other, going down the information. That gives us a number of advantages, but it isn't better for all things. So, you know, note that there are negatives as well. One of the advantages of digital is that compared to analog, where if we're sending a voltage to operate a train, that voltage is always there, and it has to vary in the real time. If we want the train to go faster immediately, we have to increase it. We can't take it away and have the train remember how fast it should be going. And the same with your TV set. You know, one channel on the TV radio band on the old analog system completely occupied by that signal. But what we can do with digital, we can send that information faster than we need to and have the train remember until we send it an update. So that means that we can send lots of commands to lots of different trains down the same pair of wires. And with your TV analogy, now you can have with one waveband channel, by sending the information, say 100 times faster than the TV needs it, you can now send 100 different channels, which is why we now have the joy of having 100 channels of rubbish on the television. But all potentially coming down maybe one TV channel, one TV radio band, should we say. So that means other messages can be sent whilst in our case, the train is responding to the message that we've sent. And also we can do clever things under the hood, which we don't need to worry about really as users. It can double check the information has come through correctly. Something you'll notice with digital, and you probably noticed this with the telly, those of us who can remember the old analog TV. If you've got a bit of interference on analog, you get a bit of haze, bit of white snow, that sort of thing, because you're seeing the messed up signal. Whereas with digital, it actually says, that's not right, that's corrupted, that's messed up, that signal, I'm not going to show you anything. So digital tends to cut out completely or be fully there. You don't get this interference, poor quality type effect. And that's true of all digital things. But the bonus is you can check it's correct. And more than one channel on a single pair of wires. So we can talk to all our different locos on the one pair of wires, which is actually the pair of rails. So moving on to how this relates to what is called DCC. So DCC stands for Digital Command and Control. So what that means is that we're using digital, using the sort of technology I've just been talking about, and we're controlling the trains by sending commands down the track. The train has to respond to those commands. It could be go faster, slow down, speed up, put the lights on, lights off, whatever. And we keep power on the track all the time because the train is only going to move when we send it a command to do so. And typically on 00, it's about 15 volts or so that we keep on the track all the time. More about that to come shortly. And we can send commands to the trains: start, speed, stop, turn the lights on, and of course we can have sound these days. We can send sound commands to the train. And because the power's on the track all the time, the lights can be on all the time. With an analog layout, unless you get very clever with the electronics, and very rarely done, basically the lights can be on all the time. So whether you can see that out behind me, in fact what I'll do, if I bring the train out, maybe that's the thing to do. So you can pin the video or just see it in your smaller one, the one that's Pete laptop. I won't actually go over to it just for this little demo. So I'm just going to pull the train out that's under the camera so you'll be able to see the end of it. And you'll be able to see the light. You can just about make out the lights coming on and off there. And I can send a command to that train to turn the light on and off. because the power's on the track all the time, even though the train isn't moving. So there's still power to work that light. And I can send a command to it to make a sound with a little speaker that's in it. Not all locos, of course, have sound in them, but that's a feature. And again, that depends on two things. It depends on the fact that power's on the track all the time, and it depends on the fact that we can send a command down the track and the loco will respond. And none of the other locos will respond, even though that command goes to everything on the layout. So that's kind of one of the main key advantages of DCC. And as I've said, the power can be used while the train is stopped. Sound, and actually one of our members in Merg Electronics group did do a train where the doors would physically open and close while the train when the train came to a station. Now, by definition, the train is going to be stopped for that, so you've got to have power from somewhere, and so that lends itself to DCC, where you have power there all the time. And auto coupling and uncoupling, those sort of things, can also be used when the train is stopped. And I haven't got it here, but I have got a little train with a little camera in the front, so you can see the driver's eye view, and again that can take power from the track and still work when the train's stationary. So having power on the track all the time is a big benefit to DCC for a number of things. Only the selected train moves. I think we've said that. So it can make the wiring a lot simpler if you're doing it in a simple way. So you no longer have to divide the layout into all these little sections. Whereas on an analog layout, if you want to bring two trains close together, there's got to be a section break between the two, just where the two trains come together, and we'll show you that in a minute. A couple of examples in my thing. This is taken at York, where you've got these bay platforms on the left and trains just almost buffered up to each other, not actually coupled. And to do that with analog, to only make the train you want, you'd have to, arrange everything over section breaks so that only the train you wanted would move. And stabling points for locos, these locos of all different lengths, all parked up right close to each other. Kind of difficult to do with analog because of the fact that each has to have its own section. And in fact, if you look at the picture, in fact, what I'm going to do in a moment, I'm going to do a couple of little demos on the actual layout. Here's another stabling point on the left, with again the steam locos all buffered up together, and you can drive just one of them off quite comfortably if you're using DCC without worrying where all the section breaks are. And if you want to add a pilot loco onto the front of your train, or coupling or dividing multiple unit trains, assembling double headers, and all of these interesting operational things that a lot of layouts just run a fixed formation train round and round, but I like to see some operating variations and have more fun with it. And all of these things would have to be arranged across a section break to do it with analog. Otherwise, you're trying to bring a loco back onto a train, a bit like this, and the wrong loco is going to move unless there's a section break between. But with digital, you only tell the right loco to move, and I'll just show that in a moment. I'll come back onto simple wiring in a minute. What I'm going to do now is I'm just going to mute this computer and switch over to the laptop. Give me a moment. Where's my mute gone? In fact, I'm going to stop the share on here and then mute myself. Thank you. I'm just going to put the speaker on here as well so that I can actually hear you. Right, so I'm on the laptop here. It seems to be right. So everybody should be now. Let me just change this to. Oh, I see. It shows my own camera. Slightly odd. Mick, can you give me a thumbs up if you can see, if you're looking at the picture of the layout on your main speaker view? You are, good, that's what I wanted. Okay, that's fine. So what I'll do is I'll demonstrate a couple of things here. I'm just going to bring this train back in from where we had it. So you should hopefully be able to see that. If I pin that to my own, I'll be able to see better. That's that. So now what I'm going to do, I'm actually operating the points from the computers. Of course, it could equally well be a normal control panel, and more on that subject later. Just So I'm bringing another train out, which will just come out under the camera in a moment. Coming out of platform 3. I'll take it just behind the signal for realism. That signal gantry isn't working yet, but the idea is it will in due course. You will see the little signal should go back to danger in a minute because I've set the route against it. So now I'm going to say, look, you do see this sort of thing on the prototype where you've got a long enough platform and your short train comes onto the end of the platform where the long train is, permissive working as they call it. Now if this was analog work layout with normal control, I'd have to arrange a section break just between these two trains, which means I could only do this with certain length trains. But I'm just bringing this onto the platform at the end of the other train, and because it has its own commands separately, I can do that and I can stop it inches from the other one without worrying about whether the right section's turned on, you know, is the right train going to move and so on. So that's an example of that. Another thing, and that's, so again, the stabling points, I mean, you can see over to the left, sorry, to the right on the way you're looking at, I think, you've got the diesel loco on the loco spur with the 9F steam loco next to it. Hardly prototypical with those particular liveries, but not worry about that. But they're buffered right up against each other to squeeze them in. And again, they can be operated independently. So that's that. One side effect of all this is that, and is different from analog, when you're using an analog layout, if you turn the controller one way or select forwards, the train will always go, shall we say, from right to left as you look at your layout. And if you do it the other way, it'll go from left to right. It doesn't matter which way the train is facing. But with DCC, the train knows which is its front. So if I were, for example, for a while, so you might need these wheels cleaning out.
Pete, we can't hear you when you're facing away from your laptop.
Okay, thanks for letting me know that. That's worth knowing. Okay, I'm back now. So you can see that the steam loco's going forwards there because I've selected forwards on the control. If that locomotive were on the layout the other way round with the smoke box facing us, forwards would still go forwards on the loco, which is different from analog layout. So forwards is always forwards from the position of the loco. So if I took this loco around a turntable or a triangle or a dumbbell on the layout, forwards would continue to be the smoke box at the front. Let's just see if I can bring that back. And the other thing I'll demonstrate here is the sound facility. This locomotive does have sound. So I can now bring it back. Whether you can hear the sound on that, I don't know.
Just.
So I've sent it a command to operate the whistle. Again, down the digital signal that's on the track. And again, I can bring this right up to the diesel to squeeze it into that bay, into that loco spur, without worrying about sections and so on. And those are the things that I personally like about digital control. Right, I'm going to switch back to the other computer, having done those a couple of little demos. So I'm going to mute it. And you should be able to hear me again now. I'm just going to get my presentation back shared again. So that's a little example of DCC in action and some of the things that you can do more easily. So let's talk about the concept of simpler wiring, which, depending on how clever you're getting on the layout, It isn't always simpler, but at the crude level, it can be a lot simpler. So hence my question mark there. We call it two-wire control, and you'll hear that mentioned for DCC. What that means is we haven't got to divide the layout up into lots of sections with wires coming for every section through a switch on a control panel. We can just take the two wires of that digital signal and connect it to all the way around the layout. Very few wires between baseboards. I mean, even this layout's a lot more complex because I've got train detection for automation, all sorts of other things, but there's still only a very small number of wires between each baseboard. So here's an example, the way you would normally do it. You have a thing called a booster, which is what puts the power on the track and the digital signal, and more on that to come. Whoops. Let's just look at that again. And typically you run a pair of reasonably chunky wires as a pair all the way around the layout, fed by the booster. And then you have your feeders or droppers from the rails on the track. And that's it. That's all the wiring you need to do for a DCC in a very simple scenario. No section switches, no isolation switches required. Trains only move when they're told to. In theory, and maybe in practice to an extent, DCC gives you slightly better running because you've always got 15 volts on the track, even if the train is going at a crawl. Whereas with analog, when you're trying to make that train crawl at a very slow speed, then what happens is that it can lose contact very easily. And if I, let me just select, I'm just going to select this one, let me just change the points again on this one. So it's, so I'm going to select the train. Again, it's behind me, but if I now make that go as slow as I can, wrong one, excuse me. You can still, it's not totally foolproof, you can still select the wrong loco and have the wrong train move. So that train, you'll be able to see it just disappearing off the end. See how slowly that's going. And with a good modern motor and a good modern digital decoder, the fact that you've got such little voltage on the, you've got the full 15 volts on the track, means that it's not trying to sort of put a fraction of a volt through there, which would be far more easily to be disrupted by a little tiny bit of dirt. So that's one factor. It does help a little bit. It's still true to say that if you've got a loco that runs rubbish on analog, it's still going to run rubbish on digital. I'm afraid it won't cure all ills, but it does just give you that little improvement as that train's creeping away there really slowly. I do like things being able to stop, and the slow running is not just a factor of it being able to run slowly. It means your starts and your stops are lovely and smooth, prototypical, rather than the horrible, you know, you see a train come along on some of the railways and you have to stop instantly, you know, all the passengers would be in the front coach. And I like to see nice smooth running. At slow speed, low current draw means that there is some energy storage in the capacitors in the decoder. Now, some decoders have additional larger storage electronic capacitors in an electronic device which stores energy. So you can actually fit what's called a keep alive to some of these, and you can actually have a loco that will continue to move for several inches, having lost connection with the track. And that, the fact that you can do that with digital, it stores that power, means that actually helps greatly on those little dirty patches, or I know for a locomotive rocking as it goes over a frog and losing contact. Doesn't mean it's 100% perfect, but it certainly improves things and has the potential to improve things. As I mentioned, keep alive capacitors as they're called. Some makes of decoders have that capability built in. Some even come with them. The bigger O gauge decoders, where they've got more space to play with, will sometimes have them pre-fitted. And some other types of decoders can be fitted with them in sort of DIY fashion, but not all. So better control. So we eliminate all the errors. I mean, you must have seen layouts that you've been watching where the train sets off from the station, another train goes smack into the buffers because the operator's forgotten to turn that section off. So it eliminates those sort of errors where you have to, you know, the operator's turning the knob and nothing's happening because he or she hasn't turned the right section on. Whereas with digital, you eliminate those errors. Although, as I ably demonstrated just now, you can still select the wrong loco and have the wrong train move. So it's not 100% foolproof. Matching locomotive speeds. Now, on analog DC control, every locomotive will respond slightly differently. Some will go really fast, some will go really slow, which, fine, you can get used to that when operating them. But then, of course, you can't double head a train with two locomotives that respond completely differently. And classic example is the Thomas the Tank Engine and Percy. If you try and that's quite a reasonable thing for the kids to run those together on a train, but out of the box, Percy goes about 5 times faster than Thomas for the same voltage. So you can't really put the two together. However, what you can do with digital is, and I'll cover this in more detail, there are settings inside the decoder, inside the locomotive, and you can adjust its response. So you can match the speeds of all your locos so that they respond exactly the same way. And now you can take locomotives that respond very differently and double head a train with them or run them together and so on. So that's all the good things, all the wonderful things I like about DCC. What about the disadvantages? Because nothing's ever quite perfect, of course. So, whereas with the analog DC control, that voltage goes straight to the motor, nice and simple, put the voltage on it, the motor turns. With digital, we've got to decode these digital commands and turn them into a voltage to work the motor inside the locomotive. So we have to fit a decoder, which is a little decoder module. I'll dig some out after the break and show you some examples of the sizes and so on of them. Tiny little circuits that actually go between the voltage and the commands coming off the track and the motor. And you have to fit one of those in every single locomotive. And actually £10, this slide was written a few years ago, and actually I think £10 upwards is a bit optimistic today. Probably £20, you find some quite reasonable decoders out there for £20 upwards, I think is a fair comment. But you know, if you've got 100 locos, that starts to be quite a chunk of money to convert everything to digital. So that is there's no doubt that is a disadvantage. And most locos, there's very few locomotives out there in most scales that can't be converted to digital, to DCC, but some of them are more of a challenge than others, and just occasionally you find something that, you know, just beats you and you can't do it, although very rare that situation. Head-on collisions now possible. I didn't demonstrate that, but of course, remember what I said, that forwards is always forwards. So let me just take him up that way a little bit. If I get him coming back very slowly, and if you can see it on the picture, that train's now coming back towards us. And in theory, I've now got those trains going in opposite directions towards each other on the same track. Fortunately, on the system I'm using, I can press the red button twice and it stops every train on the layout if I get into trouble. But I don't know how well you could see that, but because the trains are moving independently of the voltage, according to the commands, you can actually have two trains coming towards each other, which may not always be what you want. In practice, often the wiring isn't quite so simple, and I'll cover some of that. You know, once you go beyond a simple layout, and if you want to do clever stuff like train detectors and things, you start to have to add a bit more complexity into the wiring. But in principle, it's simpler. Now, I mentioned that one of the big advantages of DCC that the power was on the track all the time. That has its downsides as well. With an analog DC controller, if you have a short circuit, it only shorts that train and that controller, and only that train stops. Whereas with digital, because you've got that same power just wired to everywhere on the layout, if you have a short circuit, everything stops, not just the train that's doing the short. So that's a factor to be aware of. And whereas with your analog DC controller, it might be rated at an amp, and it's only driving the train, shall we say, that it's powering. Whereas our DCC digital system, the same power on all of the track is powering all of the trains. So it might be 5 amps or even 10 amps rated. So that much current can flow without tripping the cutout. So that has some potentials. Obviously, yeah, it's a greater fire risk if unattended. I don't think that's a huge risk, but it is just something to be aware of. You have higher current. I know someone who had a partial short In other words, it wasn't a complete short circuit to trip the breaker out on the booster, but it was drawing enough current to get things hot, and it actually melted the bogey on one of his locos that was sitting across the partially shorting. So that is a disadvantage to be aware of. It's not something I've ever really had an issue with. And what I call the burning frog syndrome, which is likewise if you've got, say, a big layout, O gauge, for example, 10 amps flowing, and you get maybe 9 amps going through a high resistance, bogey's partially derailed or something. I have known it to melt the plastic on the frog of a pico point, not on my own layout. So those are just things to be aware of, and there are things you can do about that to reduce that risk. So moving on now, DCC systems. So generally speaking, with systems that are digital command control, you have power which is some kind of AC on the track, rather than the DC we'd be used to, that controls motors directly. And somehow or other, the fireman's being too energetic in that loco, it's blowing off now. What I can do is send it a command to turn the sound off now. It's probably a good idea. Just using my little handset here to send the commands. It's easy to forget on Zoom that if you don't hold it up to the camera, people can't see what you're doing. So I've turned the sound off just by sending a command from my little handset. And so we superimpose the digital commands somehow onto that power. So we have to define what binary codes we're going to send down, not just the binary number for the speed, but there has to be a binary code that says, here comes a speed command. And this is getting into more technical under the hood stuff. But what you can appreciate is there are many, many different ways you might do that. You could have incompatibility between all things. And there were early systems, going back as far as 1964. Of course, we've probably mostly heard of 01, which was a Hornby system early on. Mayett-Klin had their own. There was a DIY system you could build in the Elector magazine, 70s or 80s, not sure, about that sort of time. Probably about the 1980s, I would say. And Lentz had their own digital system. So you can see that if every manufacturer had their own way of doing it, we wouldn't have that great bonus we have today, that we can use any command station with any manufacturer's decoders, and we buy different locomotives fitted with decoders from different manufacturers, and they all work together. I'm reliably informed, although I'm not into it myself, that in the slot car world, where they've gone digital as well, because if you can imagine having different racing cars on the same track, independently controlled, opens up all sorts of possibilities for the racing, rather than the old scale electric idea where each car's on its own separate track. But I'm told that you have to buy all your stuff from the same manufacturer. I don't know whether things have changed more recently, but basically one manufacturer's cars won't work with another manufacturer's controller. Whereas we are in the very fortunate situation. And the reason for that is that Lentz offered their system, which was a pretty good system, better than the earlier 01, as an open standard to the NMRA. Now, the NMRA is the National Model Railroad Association of America in brackets, which sets standards for model railway things. And Lentz offered their system as an open standard to the NMRA. And that was a very far-sighted thing for them to do, because what it means now is that NMRA adopted that as a standard for all model railway manufacturers. Nobody has to comply to it, but it's in everybody's interest to do so. So worldwide, pretty much all model railway manufacturers, they may have their own extensions, their own alternatives, but pretty much all manufacturers that do digital stuff conform to this standard. And that's why we have the great situation that all the decoders in all the different locos work with all the different manufacturers of command stations. So, and that, I don't think digital control would have taken off in the way it has in model railways if it wasn't for that. So how does it work? You don't have to know how it works to be able to use it. But so if this isn't of interest to you, you can have a little snooze. But if you are interested to know a little bit of the more technical side of it, about how it works, I will endeavour to explain it a little bit. So now we're talking about specifically the NMRA DCC standard. And in fact, The NMRA, in fact, I think have trademarked the term DCC, if I remember rightly. So from their perspective, whilst in a general dictionary definition, digital command control could mean any system where you send digital commands to a train. In fact, because that's a trademark term, what we really mean when we talk DCC these days in model railways is this particular system that works this particular way. And in fact, the voltage on the track, rather than being a classic AC, which sort of is curvy sine wave like you get on the mains, is actually a series of little square pulses. And if you can visualize it, it looks something like that. So there is always, let's say in N or 00, 14 to 15 volts. In O gauge, sometimes 15 volts, maybe 18 volts. In G scale in the garden, it might be 20 volts. But at the end of the day, the voltage is always exactly that much, either one way or the other. The pulse changes polarity very fast, many thousands of times a second. And that can be used by the decoder just to generate power. So it's always got power off of that signal to power the locomotive, to power the lights, to power the sound, to power everything. And then what happens then is, how do we put the commands onto that power signal without the power messing up the commands? And what we do, the pulses are actually varying in lengths. So remember, going back to our binary discussion, all we've got to be able to do is send a 0 bit or a 1 bit, and then they get built up into numbers and commands as they come one after the other. And so what we do here, if the pulse is short, you can see my cursor there, then that's a 1 binary bit. If the pulse is long, like twice as long or anything longer, then that's treated as a 0 bit. So they come along one after the other. The decoder, as well as getting power from that signal, it can decode all those pulse lengths, decode the ones and noughts, turn those into numbers, turn those into commands, and know whether it's got what it's got to do. Don't worry about the stretched 0 bit. That's a more technical thing, which is a bit beyond the scope of today's talk. But basically, just worry about the ones and the noughts. So, so what happens is that it will send, for example, using that scheme, it will send the locomotive number. More about how we assign that later. It'll send the locomotive number, so it knows every other locomotive will ignore the command, and then it might say another command that says put your lights on, or another command that says go at this speed, and the number will be there for the speed to go at. And the little tiny computer effectively inside the decoder works all that out, and then sends it has some electronics in it as well that controls the voltage to the motor, and it responds by sending that. So that's kind of in 2 minutes flat how DCC works. Obviously there's a lot more to it than that when you get down into the details, but that just gives you a rough idea of how it combines the commands and the voltage on the track, because that's the trick. We've only got 2 wires because there are only 2 rails in most scenarios, and therefore we've got to get the power to the train and the signals and commands to tell it what to do down those 2 wires. So to get started with DCC, what do I actually need? Well, you need some sort of handset or cab. I'm using the Merg one, which looks like this. You build that one from a kit. Of course, there are many different makes out there, and they're all compatible with the decoders. So it's variously known as a cab or a handset or a throttle. I'm just going to tell this lady I'll call her back in a second. Hi, Judy. I'm just giving a talk to the Missenden crowd. Can I call you back in a bit? We'll take a break in about 10 minutes or so. Yeah, all right. Sorry about that. So, cab or handset or throttle. And then we have what's called a command station. And that's a box of electronics that takes the information from the handset or throttle and creates that digital stream of noughts and ones. So when if I select a locomotive on here, by typing its number in, then the command station will create the command that says this is in binary, select this locomotive. And if I turn the knob, it'll then send the command out that actually tells the train to move. We don't have to worry about how it does that. I mean, there are some systems, so I remember the make of it now, the early British one, which had that integrated into the panel so the handset wasn't separate, but it all works the same effectively. Then you need what's called a booster. And what a booster does is it takes that binary signal produced by the command station, it's only going to be sort of 5-volt signal, and it combines it with that square wave we saw with the bigger ones, bigger pulses and shorter pulses at the voltage you're working at. Now, quite often the command station and booster are combined into one box, and to you it's just a command station and booster combined, but they can be separate as well. And the booster is what actually provides the amperage to drive all the trains on the layout, because unlike your analog controller, which only drives one train at a time, the booster has to have enough oomph to drive all the trains on the layout, but more about that to come shortly. And then we need decoders in every locomotive. That's what I need to be able to run digital. How do you connect it up? Well, we looked at that briefly earlier. Let's look at a little bit more detail. So we have our handset, which plugs into the command station. And on a typical layout, you'd have multiple handsets, perhaps distributed around the layout. So there'll be some wiring between the handset, all the different handsets, typically a common set of wires back to the command station. That's another story for another time. We have our booster, and again, these might well be in the same box, the command station and booster. And we can plug that into an existing layout. In fact, we can just turn all the section switches on and feed the booster in where we would have fed in our analog controller before. That's not optimum. There are some technical issues with doing it that way, but you can do it with a smallish layout. Alternatively, as I told you earlier on, you would tend to connect that booster to a pair of chunky wires to carry the current going around under the layout. Various different ways people do that in terms of what the physical incarnation and how you join everything together. And then you run droppers from all the different pieces of track onto there. And that's the simple way of wiring it up. On a big layout, you then have some issues, because on a big layout, you're asking an awful lot of current out of the one booster to drive everything on the layout. And you remember what I said earlier, if you get a short circuit anywhere on the layout, everything stops. So we can introduce the concept, and now we move slightly away from the simplicity of it only being 2 wires, of what we call a power district. So we have another booster, and that's driven by the same command station. It actually drives both. There should be another wire there, really. And it sends exactly the same signal as the first booster. And now we have another part of the layout which has its own pair of wires and its own set of dropper links. They're getting both sections of the layout, both power districts as we call it, get the same commands from the same command station. So a train will move quite happily, whether it's in whichever section it's in, if it gets the command. But a short circuit now in one of those power districts will not cause the other one to stop. And now the booster only has to cope with a current that might be run in one section. You might, for example, have a marshalling yard where people are more likely to short things out as they're shunting around and perhaps not setting the points right. And it could be its own power district, so that a short circuit there doesn't stop the main line. Might be the sort of thing you might do. And you can develop that theme and have as many of those as you want, power districts, within reason. I mentioned the decoders in the trains. And they have inside, they have settings. Now, because this is of American origin, settings is too short a word. It only has 2 syllables. So the Americans like configuration, variables. There's about 10 syllables. That's better. I hope there's no Americans on here being offended. But so they're known as CVs, whereas actually they're just settings inside the train. So the way the rate it accelerates, decelerates, the maximum speed. So in fact, when I was, I'm just going to do a hand of God here and push that locomotive back. So if you can see either on the little picture, which is peak laptop, if I actually put this locomotive to full speed with the knob, and I'm just going to go whang, full speed, but it accelerates away nice and slowly and gently, because that's one of the parameters that's programmed into the decoder chip. The decoder chip says, okay, I've got to go to full speed, but I'm going to do a gentle acceleration to get there. And you can program all those parameters however you like, and it can be programmed from the handsets, or you can do it from a computer. And again, that's some of the stuff we would normally have got onto on the second day of a weekend course, is programming all the settings and changing all the settings, all sorts of things you can set there. And also how fast it responds to a particular speed and what voltage it actually puts to the motor for different speed settings. And that's how you can match the speeds of different locomotives so they all respond the same, so you can double head with them. So motor control parameters, lighting control, how the lights work. If you're a US outline modeler, you can do all these flashing ditch lights and all the clever stuff that you would have for that. It tends to be simpler on our own. And as I say, the command station via the handset, but you have to know all the codes to be able to do it that way. Whereas there is also a program called Decoder Pro, which you can run on a computer connected to your layout, which means that you don't care what all the codes are. You just tell it acceleration, deceleration, that sort of thing. You do it in English. That's something we would get onto, yeah, in that sense. We've talked so far about controlling trains because that's where the key advantages of digital are. We can reduce the wiring. We don't need all those section switches. We don't need the wires for every section going across baseboard joins and these huge great connectors with 40 or 50 wires in. We can just have the 2 wires going across the join to control the trains. So mobile decoders, as they call them in locomotives, is where the key advantages of DCC are. But DCC can also be used to control your accessories if you wish. So I'm talking about turnouts or points, depending on terminology you're using, signals, turntables, line side equipment, level crossings, you name it. Now, with a DCC layout where you're controlling your trains digital, you can still control all those accessories any way you like. It can still be wire in tube, mechanical, manual. It can be wired the standard analog way with a wire from it to every point back to every switch. You can still do it all that way. You don't have to go digital with the accessories just because you've done so with the trains. But there are benefits in doing so. So what I'm going to call the conventional DCC way, so I've mentioned the analog way where you just do it the way you always used to. So what we can do here, we've got our command station here with the handset as we talked about before, and that's feeding onto the track. And as we can see on the right hand side, we've got a mobile decoder inside our train, and that's what we've been talking about so far. But we can also have connected to the same track, we can have what's called an accessory decoder. That doesn't have to be so small, it can be a lot bigger, and because it's only got a mount under the baseboard, and that can control the points and the signals and all these other accessories. The advantage of doing that is that now we haven't got to run separate wires to this. It just takes it off the track, so it minimises your wiring. The problem is, there are several problems. Most analog layouts where you've got your switches, you'll use a mimic diagram with the switches in the right places on the mimic diagram. So or push buttons or a contact start or whatever it is to change your points to set your signals. Most commercial command stations can't do that with points and signals. Some of the more expensive ones can. There's the Viessmann and the somebody will tell me the name of it. There's one that's got a little touch screen actually on the display, but those are expensive beasts. And of course there is a move maybe towards using computer screens with it. But most of them, you would have to say, you know, this is turnout number 123 on my layout. I'd have to type in 123 and say change that one, which isn't very intuitive for doing it. So that's one disadvantage. Some systems do have the ability to add a mimic diagram linked into your command station to do that with. The other disadvantage of doing it this way is that, well, two disadvantages really. It's drawing current from your main booster as well to operate the accessories, so you have to make sure that's big enough. The other problem you have is the classic short circuit situation is where you change the points the wrong way, and as the locomotive comes into the points that are set against it by mistake, you get a short circuit. Now, if your accessory decoder is relying for power from the track to change the point, you now can't change the point back because you've just shorted out what powers the point. And you have to, hand of God has to come in, move the train back, and then the power comes back on and now you can change the point. So that's a disadvantage of doing it this way, is that all your signals are going to go out every time you have a short circuit, for example, which isn't great. So there are disadvantages of doing it this way. Now, there is an alternative way of doing excessive control with DCC, and that's to keep your accessory control and your power completely separate. It's accessory control and traction power, I mean, for the trains. So what we would do in this case Here we have the scenario we just talked about just now. And here we've got the track connected to our accessory decoder. Well, what we're going to do now is have a separate mimic panel here, mimic diagram, so we can control the layout intuitively. And we break this connection here. The accessory decoder is no longer connected to the track. And what we do is we have what's called an encoder that actually is effectively a command station just for the accessories, but it works in exactly the same way. And we run an additional pair of wires around the layout, which is, so we've got our two big fat wires for the DCC, known as the DCC bus, for the track, and a separate set of wires for the accessories. So yes, we've increased the number of wires, but it's still nowhere near as many wires as one from every switch to every decoder. And now we connect that to the accessory decoder. Because this works to the DCC standard, we can use all the same decoders we would have used had we been connecting it to the track. And now we don't have to worry about this drawing power from the main track bus. And if we short out the main track, we haven't shorted out our accessories. So a short circuit on the track, the signals don't all go out. And we can, if we run a train into a point the wrong way and short it out, we can change the point back without having to fiddle with the loco because we've still got power. So if you're going DCC for accessories, certainly recommend that possibility. There is another alternative way. Oh, no, this is just a summary, my apologies. So we can control it from the mimic diagram now because it's separate and it works with the standard accessory decoders. But you can still really, in a simple term, you can only have one control panel, one main place, because one of the parameters of DCC is that, in the general terminology, without going into too much technical detail, is that because it's sticking the power on the same pair of wires as the signal, it's difficult for anything else to send a message on that thing. You can't have another control panel. So there's what I call an even better way of doing it. If you're going digital, it's still digital, but it's not DCC anymore. We have what's called a layout control bus. So those extra two wires that we ran just for our accessories, they're not DCC anymore. They're what we call a layout control bus. They're still a pair of wires. But what we can do is it's more flexible and it's independent of the track power. Your track can be digital or analog, doesn't matter. But it's still worth doing your accessories this way. And Merg have a thing called C-Bus. There's Digitrax have one called LocoNet, which is quite widely used throughout the world. Lents, the originators of DCC, have their own one called ExpressNet. And they're just different standards, different ways that these work. The difference is that you do have to have, instead of a DCC decoder, you would have a decoder appropriate for your particular bus that you're using, a LocoNet one, an Express one, or in our case, a C-Bus one. And that's a whole other story of how you would control the layout using one of these layout control buses. But just to make you aware that that's an alternative digital technology purely for the accessories, independent of the trains. So that's my quick intro to DCC, what it is, how it works. So what I'm going to suggest, I see there's a few things, few messages in the chat, but what I was going to suggest now is that we have a break for, shall we say, till past. Mick, does that sound about reasonable?
Yeah, that sounds okay, Pete. Yeah.
Yeah, we've generally found.
Sorry about the delay. I had to unmute myself.
Yeah, I could say I was waiting. I could see you doing that. That's fine. Yeah, because what we found with these Zoom meetings, I think a break of 10 to 15 minutes every hour avoids the fatigue from staring at the screen too much. So, and then after the break, we'll take any questions. I suggest we work through anything, any comments and links in the questions. There aren't too many questions actually, and then we'll take questions from anybody and anything on anything to do with DCC, and if I know the answers, I'll try and answer them. So I guess first questions specifically relating to the content of the presentation, and then we can move on to other subjects as we go along. So is that okay with everybody? Some thumbs up.
Yeah, thank you.
So
thumbs up. Yeah. Okay. Jolly good. Okay. Thanks, Pete.
Thank you.
No problem.
See you in about 15 minutes.
Yeah. So
Lovely.
I'm
Thank you.
about 15:15. Yeah. All right.
Okay. Anything you say now is on record.
Okay. So, well, I guess just general Q&A session. I'm just seeing if there's any specific questions in the. Oh yes, Greg answered my question. Greg always answers my questions that I can't think of. So, what time is it? I don't know what time it is there at the moment, Greg, but it must be.
He's gone.
He's gone. Oh, well,
Yeah, he's gone. Crash.
late into the night, I expect, probably that because Greg's in Australia. So, but the one I couldn't think of, the early British DCC system, that instead of having a separate handset, it's all on the main console. That's the ZTC system. And the early ZTC systems and decoders weren't 100% compatible with the standard, so there were some problems. But I think the later ones were. I've got a message from somebody that says on or off. I don't know what that was in context with, because I wasn't looking at these at the time. So, and another one from Ian that says yes. So I don't know what that means.
I think the first one. I think the first question that needs an answer, Pete, is from Basil Stevens.
Okay. Oh yeah. So he's used JMRI and connect 2 sprogs, 1 on booster, 1 for mega. Okay. So the question is from Basil. So he says what he's done is use JMRI. Now JMRI is a computer program that you can download for free and can be used to control a layout. The automation you saw going on my demonstration layout with trains going backwards and forwards is all controlled by that particular program. It also has a part called Decoder Pro, which allows you to program the settings in a DCC loco. And B, connect 2 sprogs, 1 a booster, 1 for locos, and the second for accessories. Yes, so he's done exactly that that I suggested, where you've got the 2 separate DCC circuits, 1 for the track and 1 for the accessories. And he's controlling it from a computer program that can have, it can, if you want, have multiple connections, 1 to control the accessories, 1 to control the trains. So those are other ways of doing it if you want to go down the computer control route. Of course, DCC doesn't depend on computer control. It's just one of the things you can do with it, because all of your trains and accessories are now common on these pairs of wires. It becomes quite natural to be able to connect it to a computer and have your control panel on a computer, either instead of a physical control panel with buttons and switches, or as well as indeed, is what I have on the layout here. So, so he's got a thing called a sprog. A sprog is it started off as a little, it can work as a little command station and booster. It can also be used as a programmer for the settings in a loco, and there are newer sprog products coming along that work with other things. And certainly he's got 2 of those, as I say, 1 driving the accessories and 1 driving the track. So effectively it's 2 little command stations, 1 for each. And I mentioned this idea of wanting to have a mimic diagram. And that's more amenable if you've got a separate bus for the accessories. And of course, that mimic diagram can be a computer one if you have the knowledge and the ability to set up a computer program. JMRI is one of the better known programs for doing this sort of stuff. It's a big learning curve, but it's free. Okay.
And the next one's from Gary Day.
Yeah. Yes, between power districts. So because the boosters are putting power and signal out to both those sections, you do need a rail break both sides. Because it's the same signal going to both, just being generated by 2 separate boosters, they're in phase with each other. In other words, one's high, the other's high and low. So there's no problem as a train or loco bridges the gap between the 2, because they should be at about the same voltage. I mean, it is wise to adjust both boosters in a power district to be about the same voltage output. But basically, yeah, a double rail break, in both rails between the power districts, so that the signal is isolated between the 2. Hopefully that answers that question.
There's one from Tony Montgomery.
Yeah.
About short circuit protection varying.
Yeah, so yes, it can vary. I know the big NCE booster, 10 amp thing, doesn't seem to cut out completely. It just seems to limit to 10 amps, and I've seen smoke and sparks from something driven by one of those. In terms of standard, I think what you need to do is ideally have it tripping out when the current exceeds what your layout will normally give in a normal way. So if with all the trains going at once on your layout, you're drawing less than 5 amps, then have your trip set at 5 amps. Now, an additional thing I didn't mention that you can do, as well as having separate boosters for your power districts, you can get a little circuit called a district cutout. And it's not a booster. All it does is it cuts out faster than the booster. So you can connect, say, a particular yard or a particular smaller area through one of those. And that can then have a lower current trip, so that if you get a short circuit just in that area, it doesn't short out the rest of the power district. So it's different from a booster, because a booster is actually supplying separate power. So Tony, am I understanding the question correctly, and have I answered it at all? We need to unmute yourself, or somebody unmute you.
Oh, he's giving you the thumbs up, Pete.
Okay, so that's answered the question. Okay, that's good. How do I standardize functions for sound? Yeah, that's a thorny one. Because I mentioned the NMRA standards and how we're lucky that everything works the same. But the standard only went so far and was all written before sound came along. So manufacturers did their own thing with sound. So actually the settings inside the loco, the codes are different, and which function does what. Now, most decoders, particularly the more sophisticated ones, such as ZEMO, ESU, CT, you've got a lot of control by changing the settings inside these CVs as to which function does what. It's not simple or trivial, and it's easier if you're using a program like Decoder Pro, but you should be able to change, for example, taking your example, the whistle always on function 3. So by changing the settings in the decoder, you can mostly achieve that. I say mostly because you take something like the Hornby TTS cheaper sound decoder, that has much less capabilities for modifying things than the more sophisticated ones. So you may find that you can't always achieve quite what you want. And the other complexity is, it's simple to say, yes, let's make always F3 the whistle. But most decoders will have about 4 or 5 different whistles you can make. And another decoder might only have 2 or 3, and they might be different variations. So trying to standardize with different decoders doing different things, you know, and you then throw a diesel in and say, well, F3 should be the horn, but then you might have one function does a da-da, and one other function does a da-da, and another function does just the low, and the other function does just the high, so you can combine them. And so there's so much variety in decoders that does make it a bit of a challenge to get them all to behave the same. And most people end up with sort of a crib sheet on the layout that tells them what function does what for what loco, because they ain't all the same. But you can, you know, you can get to a level of commonality, you know, within what you can do. And they're not standards, there are conventions. So the convention is that F0 on your handset, function 0, will always turn the main lights on and off, the headlight and so on. F1 in the UK is generally used for turning the sound on and off. F8 tends to be that in America. And then you will find quite frequently that the next few functions above that will do the whistles and the sounds. But then along comes a simple decoder that doesn't have sound, and you'll tend to find all the lighting functions will be on F1, F2, F3, which on the sound decoder are used for sounds. And sometimes those simple decoders don't have the ability to put it on a higher number. So it's a bit of an intractable problem. And people have come up with schemes where you get clever handsets that you pre-program with the response of a particular loco, and JMRI can do that to a certain extent. JMRI has an interface that allows you to actually use your smartphone as a handset on the layout. And you have got options there for sort of translating functions and things, and also for the function button to show what it does. But there isn't a perfect answer to that question, because there's so much variety between decoders, sound and non-sound, and amongst different sound decoders. So you can go some way towards it with reprogramming and create your own standard for which function is going to work the whistle. So you've got these semi-standards for some basic functions, but once you go into which button works which sound, you've kind of got to create your own standard and try and modify the decoders as best you can to fit in with it. So any other questions sort of arise out of that discussion?
I'll send a message to everybody, Pete, saying that if they've got further questions that we can't answer during this session, they can write them onto chat and we'll pick them up and respond to them later.
Yeah, okay.
The next one is from Derek Mothers.
Oh yes, bus. Yeah, interesting one that. What does it stand for? Doesn't quite stand for anything. Interesting one that. What is a bus? So before we had digital, you had to have an individual wire for everything. You know, one wire for every switch, one wire for every block section. And this happened first with power, where rather than having an individual wire to power everything, you could have a big fat common wire that would power everything instead of lots of individual ones. And that was known as a bus bar. And it doesn't stand for anything. It actually comes from the same derivation as the double-decker bus, surprisingly enough, because back in the early days, people had private carriages, and then along came the omnibus, omni meaning for everybody. So the omnibus was invented as one to do everybody. And so must have been a Cockney rhyming slang person that when they invented the bus bar, instead of using the word omni, should be an omnibar, they used the second half and called it a bus bar. So we have in the early technology, you know, 40s and 50s, we have power on a bus bar because it's common, derived from omnibus. So when digital technology comes along, now we don't need one wire for every different signal. We can put multiple signals down one wire. Hence it's known as a bus because it's an omnibus for everybody. So that's the derivation of the term bus. So really one set of wires that has multiple different signals going down it, as in all our different commands. The locomotives go down this pair of wires, which is known as the DCC bus. And then if we've got a common pair of wires for accessory commands, whether it's by DCC or some other bus standard, they're still referred to as the accessory bus, if you like, or the layout control bus in more wider terminology. So that's bus.
We have a question from Beavis Heap.
Yeah, there's a second part to Derek's question. Shall I just finish on that one? He was asking, should bare copper wire be used for them to make soldered connections easier? And I have used that approach in the past. The downside, of course, is that they're bare, so if things touch them, you get a short and so on. Certainly people have done that. I tend these days to use normal wire, reasonably flat, sort of very loosely twisted together, so I can, just to keep them together, and then I can pull a loop out and put the sideways wire strippers and just pull a bit open and then solder a dropper onto that. That's the way I do it these days. And I found that works well for me. I prefer that to having lots of connectors, crimp connectors, all that sort of thing. But yeah, the bare copper wire can work, but you've got to mount it carefully so it doesn't float around and things don't short against it, I think is the answer to that. There are as many different ways as wiring up DCC buses, I think, as there are modelers almost. But one thing I will say, and we cover this very much in our detailed C-bus course and so on, is do not use mains cable for your DCC bus. It's a very tempting thing to do because it's just the right size and shape and power carrying capability. But the thing is that we're all conditioned that when we see mains wire, that's dangerous, we don't touch it. If we start making a habit of using mains wire for our low voltage connections, we've turned off that safety thing. So one day we might grab hold of a wire thinking it's only our DCC bus and it's actually a mains one. So as a general rule is we should only ever use the wire for what it's intended. Don't use mains wire for low voltage wiring under the layout, even though it might be cheap and attractive to do so, is my very strong message for everybody. Did have an incident once where somebody who's quite happy for me to relate this so other people can learn from it. His accessory control was powered by 15 volts AC, and he'd used mains twin and earth for it, or mains twin for it, with a pluggable chocolate block on the end. Fine, the chocolate block's fine, but not fine using the mains wire. He was running it from an old Hamilton Morgan controller to produce that 15, 16 volts AC to control his accessories. And the mains lead on it wasn't long enough. So he extended it using identical mains twin as he'd used for his low voltage. And big mistake as well, he'd used the same kind of pluggable chocolate block. So of course, when he was setting it up here to do some stuff, he picked up the mains end and plugged it into the low voltage end, bang. Luckily, no one was touching anything at the time because someone could have been killed. But it burnt out tracks on the circuit boards and big lot of smoke. So, one of the mistakes there was using mains cable for his low voltage wiring. So that's just a message for while we're talking about DCC buses and things, because you do, one of the magazines I think even recommended it, which I thought was appalling, that you know, using mains twin for your bus is definitely a no-no. So okay, so sorry, Beavis was the next one you were going to suggest.
Yes, he's asking about something that is quite keep alive.
Yeah.
I'm
Yes.
wondering if that would be best answered.
Well, I can touch on it
Okay.
for the more technically inclined. So the idea of a keep alive capacitor. So a capacitor is an electronic component that stores energy, and the physically bigger it is, the more it'll store. And some makes of decoders, such as the Zemos, actually come with a little one, and you can fit a bigger one if you fit it in the loco. I did an O-gauge saddle tank for somebody, and I found that I put a capacitor that was the diameter of the O-gauge boiler and slid it down the boiler, and it was a big value, and the thing would go more than its own length with you could put a bit of paper underneath it, and it would quite happily just chuff over the bit of paper to the other end. So and that means, again, the benefit of that is that if you get dirt and muck on the track, or a bit of loss of contact as you go across the points with it rocking on a short wheelbase loco, it'll just keep going. Now, DIYing it with decoders that were not designed to have it, sometimes it works and sometimes it doesn't. You've got to find out in the circuit where the internal power rail is, and there is some stuff on forums online on how to do this, and you need to put it's a bit of electronics to do, because you've got to put a resistor in series so it doesn't, if you've got too many locos with keep alives, they can draw so much current when you turn the layout on that it just trips out the booster. So you put a little resistor in series to limit that current, and then you need a diode going the other way to make sure that it can draw current out of it quickly. So you do have to get into the electronics technicalities a little bit. You've got to find the right place in the circuit. And even then, it works with some decoders and not with others. And the reason for that is that some decoders that weren't designed for keep alives, if they detect that the DCC signal has gone, they just stop anyway, even if they've still got power. Because most decoders will work with analog DC as well. That's something I didn't mention. If you've got a locomotive fitted with a digital decoder, a DCC decoder, and it detects that it's not getting that square wave, it's not getting the commands, it's just getting a variable DC on it, it'll say, oh, I'm on an analog layout, I'll just respond as though like an ordinary loco. And kind of you have to turn that off in the settings for keep alive to work effectively, because what happens is, as soon as it sees that it's not getting the digital signal anymore, and if it's getting 0 volts, it thinks, oh, I'm on an analog layout, and 0 volts means stop, so it stops. And some decoders will do that anyway, even if you fitted a keep alive. So it's very much a suck it and see. After you've blown up, you'll probably have to blow up a few decoders to get it to work. But by all means, have a go if you're technical enough to get into that. Does that answer that question to an extent for those who are familiar with what we're talking about? Can I introduce the Sprog? Well, I'm not an expert on the Sprog. The Sprog is Andrew Crossland, who's one of our Merg members, designed the Sprog, it's a small device that connects to a computer. So it doesn't have separate handset, separate control panel. You connect it to a computer. The early Sprogs were USB. I think he's also maybe looking at Ethernet and other things now, or C-bus. But basically, it has a USB plug on one end and the layout connection on the other, and you control it entirely from the computer. And you can use software such as JMRI. I think it did have its own software early on, did it? I can't remember now. It's a long time since I fiddled with one of those. So it can be a very cheap way of getting started. If you look up Sprog DCC on Google, you'll find the information for it. And so it's a very low power programming device, but you can also use it as a low power command station. And then you can add boosters to it. And I think Andrew's doing his own booster designs as well to go with it. So it's a little family of DCC capabilities. I mean, likewise, for those who are members of Merg, which is Model Electronics Railway Group, Merg makes kits of parts to build electronic bits and pieces, and a DCC handset, which is this one, and a DCC command station and booster are amongst those parts. And so a fraction of the cost of going and buying commercial, but you've got to be prepared to solder it up yourself. So that's the pros and cons. So you've got the Sprog, which is a reasonably cheap, ready built, ready to go. you've got the kit base from Merg, and then you've got all the other commercial offerings, and that kind of leads on to choosing which system do I use, and really it's which one you like to work with, which one you like to play with, as it were, which has a handset that you're comfortable with, that's easy to use, intuitive to use. I find the Merg one's very intuitive. I find the Digitrax and one a little bit less intuitive because it's got lots of little black buttons all the same. But obviously, like all these things, once you get to know them and you get familiar with them, they do the job. Because one thing just to mention, we've got this standard that means any manufacturer's command station and kit will work with any decoder, but the standard does not extend to how handsets actually connect to the command station. So mostly, with only very minor exceptions, you have to use the same make of handset with the same make of command station.
Can I just ask, additionally on that, the relationship between Sprague and Decoder Pro? I've got a ZTC system, which I've had many, many years, but not used for the last 10. And I was just wondering whether to do some development work on that, whether to use a Sprague system attached so that I can use my computer.
Yeah. If we're talking about the JMRI software, which is Decoder Pro, that will talk to pretty much any manufacturer's DCC system that has a computer connection. And so the Sprague is one of many, the Merg system, LocoNet, Digitrax. So once you've got your programmed command station, whether it's a Sprague or a ZTC or whatever, linked to the computer and linked to the layout, Decoder Pro works the same, whichever one it is. One of the things I didn't cover is this distinction between programming track and main track, which is something we go into more on when we do the main course. But so you have this distinction between the main layout, which is where the trains run, and you can send commands to change settings, but you have to know which loco you're sending them to. And then you have a programming track where you can also read back what the settings are, because you can't on the main track. You read back what the settings are. You can set the locomotive's address, which typically be the locomotive number, or I tend to use the class number, which is how you select the loco. And the Sprague will do either. I think the newer ones possibly both, because Andrew Crossland, as the Sprague designer, he also designed the original Merg command station as well. Sorry, he did the software for it. Mike Bolton designed it. So some systems will have both the programming track and the main track at the same time. The Merg one can do that if you're using a booster, and some will be one or the other, and you have to switch it. So, it doesn't really matter from the once you've got it connected up and working, whether it's a ZDC or Sprague or whatever. Oh, I'm just getting presented with a croissant and a drink. Thank you very much. Lovely. So Rob, does that answer the questions? Yeah, okay, I'm getting 2 thumbs up. Must be good. Right. Right. So Peter Jackson, with the separation of control and layout bus, is the layout bus still connected to the main command station, or do you have a separate command unit? Right, depends. One of those answers. So the separation of control and layout bus. So you've got your traction connected to the track connected to the command station. Then your handsets have to connect to the command station somehow. Now, quite a lot of systems, and Digitrax LocoNet does this, and the Merg C-Bus does this, use the same layout control bus to actually connect the handsets to the command station. So the command station is connected to the layout bus, but purely for the reason of receiving commands from the handset. The accessory commands conceptually are separate. I mean, you can get into more complicated nuances of that. So the layout bus would only be connected to the main command station if that's the way the handsets send their messages to the command station. If the command station just has a separate directly plugged in handset, or like the ZTC has its controls directly on it, then no, you wouldn't need to connect the command station to the layout control bus at all. Does that answer that question for Peter? I can't see Peter's picture on here somewhere because I've got 37 people.
Not quite.
Yeah.
I've got an NCE system with
Yes.
boosters on,
Mhm.
and have usually used the track and the accessory bus combined. So if I wanted to separate them, what do I need to get to control the accessories?
Good question. Excuse me, I'm just having a bit of croissant. So how are you changing the points at the moment? Are you doing it from the NCE handset?
Yes.
Right. So in order to be able to change the points from the NCE handset, the decoders for the points kind of have to be on the same, connected to the track. If you were prepared to go down the route of having a separate, let's say, a layout diagram, and change the points off the mimic diagram and not change them anymore off the NCE handset, then that obviously opens up your possibilities quite a lot. You could go with something like the Merg C bus. You could go with a Loconet-based system. NCE do have systems, and I can't remember whether it works off the same cab bus. There is an NCE cab bus, and it may be possible to operate NCE type decoders from there. But if you're using generic DCC decoders and you want to separate the command from that, my understanding is that the NCE, I'm not an expert on the NCE, but my understanding is that the NCE cabs wouldn't drive that separately. But what you could do is use a Merg have a system where you can have a mimic diagram and it just sends standard commands. The decoders for the accessories on your layout, are they different makes or mostly NCE ones? Or I think you may be muted again, Peter. Can't hear you at the moment. Okay, well, I shall carry on doing my best to answer the question.
I lost him completely.
Yeah, oh, well, never mind. Is he still on the meeting, or has he dropped out?
Oh, I can't see him.
No, he may have. Maybe he's got an internet issue or something. But yeah, so for everybody else, is probably so to take a layout that currently has the one bus and all the decoders. Are you back? You're back, Peter. We lost you. So do you just unmute yourself, and then how much of my answer had you heard?
Virtually none of it, unfortunately.
Okay, well, I'll just reiterate it. So you've got a situation where, and are the decoders mainly NCE decoders for the points now I'm talking about, or different makes? Or
Cobalts.
Cobalts, yeah, the Cobalts with the built-in DCC decoder, presumably. Yeah. Okay, so at the moment, the NCE handset is sending those commands down the NCE cab bus, if you like, to those, to the command station, and then down the track. It goes down the track to those. So if you wanted to separate, you'd run your separate set of wires, and it would need to be DCC if you're going to continue to use the Cobalts in the same way. To those, so now you've got your separate accessory bus. You would need something to drive that accessory bus, effectively a separate command station for the accessories. Merg certainly do a kit for something that will do that, and you can have a mimic diagram, and you would change your points from the control panel rather than from the handset, which personally I think is probably easier. I'm not aware with the NCE system of an easy way, and there are ways, an easy way of having the handsets continue to be able to change the points on the other bus. However, if you were going down the route of having something like the JMRI software sitting on a computer in the corner, and of course the layout would still work without it, but that could be programmed to take the commands off your NCE handset and forward them onto the accessory bus that you've created for just the points. So you can do clever things with that. So it's fairly techy getting into that. And I'm not sure what other. I mean, you could just put something like a Sprog in. Would drive the accessory bus, but then you would need the computer control panel to drive it, because it doesn't work so much with a physical control panel. So there are a number of different choices, and it depends on how you want to operate the points, whether you really want to continue operating them from the NC handset, or whether a control panel would be a better way to do it.
Right. Okay.
Diagram on it, so it gives you there's some ideas there.
Yeah. Thank you.
Okay. Scroll on down the questions. For automatic control, are there any basic non-system rules? I'm not quite sure what you mean by non-system rule. For automatic control, you have to be able to detect where the trains are and where they're going to stop. Otherwise, by automatic control, I guess we're talking about computer control. So the layout here is fitted with block detectors, which measure current. And so the droppers, going back to my earlier diagram where we had the droppers going onto the common bus. So one of the rails for each block goes through one of these little detectors. So using our layout control bus we talked about earlier on, a message goes, because the advantage of a layout control bus for accessories over DCC, which I didn't mention, is that with the DCC accessory bus, you're only really sending commands out to change points, to change signals. With a fully flexible layout control bus, you can get signals back into your computer or whatever from things like train detectors, so it works both ways. So this has block detectors on it, so you know whether the block is occupied or not, so the computer can track the train from one place to another. So you certainly need train detectors, and I also have it close to the buffers behind me, some little infrared optical detectors, so the train gets there, we know exactly where it is now, not just the block's occupied, and it can be stopped accurately at the end. So I think the first prerequisite for automation is train detection fitted throughout the layout, and you have to think about how you divide it into blocks. And then depends on what software you're going to do the automatic control with as to what all your prerequisites are. The JMRI system, you've got a couple of options. You can write your own little script programs to do the automation, which is what is happening here. There's also a thing built in called the dispatcher, which does operation. Now that drives the trains to the signals. So now another prerequisite is all your signals have to be working properly before that way of automation will work. So there's kind of a bit of getting all your ducks in a row. The computer also has to know which train is where. And you can either have a system where you type that in, where I do on the, let me just share that. I'll share my screen here. Let me just show this. I mean, this is going rather beyond introduction to DCC, but as we're in the Q&A session, we can digress. That's allowed. Let me just bring this up. So this is actually the layout diagram from my JMRI. So the red is where there are trains being detected as that block is occupied, because another thing about DCC compared to analog is that the decoder still draws a bit of current even when the train's stationary, even if there's no lights on or anything, and that current can be detected by the little detector we put in series with the dropper. So that sends a message back, and the software gets that message and says, right, this block here is occupied. It doesn't know exactly where the train is, but it knows it's occupied there somewhere. And then the little indicators here show that the spot detector at the end, the infrared, is activated, so that means there's a train right up close to the buffers. And then I've got signals and things here as well. So I just written a little script program that drives the trains backwards and forwards, but you can use the all singing, all dancing dispatcher, but everything else has to work perfectly before that'll work. And then I've got these little things here where I tell it what train is where. So I can actually type into there and tell it train number 158, which is my class 158 DMU, and that's the DCC address. Every locomotive on DCC has to have a unique address, and that's what you select on the handset. And so the computer has to send the commands to that loco as well for automation. So you just have to have a way of telling it, and the very simplest way is just to type it in, and then the computer tracks it as it goes along. You can also use RFID, which is little tags that go under the loco to identify them automatically. But that's a whole other subject again. You know, you're getting into a lot more techie stuff than just beginners DCC then. Yeah, for automation, you need some software, you need a computer control connection, and you need train detection so the computer knows where everything is. And then you need a way of identifying the trains at the beginning, which can be as simple as typing it in. And different software does do it different ways. JMRI is the one I'm most familiar with. Does that answer that question? And dividing the layout into blocks, because you're putting a rail brake and making sure the dropper the current goes through that when the train's in the block. So working out how you divide it into blocks, and that's something we cover when we do our JMRI course as well, as to how you divide it up into blocks and where you put beginning and ends of the blocks.
Thanks, Pete. Much appreciated. I use iTrain and DigiKais and LocoNet.
Yeah. So a lot of the same rules would apply. I mean, Yeah, some software kind of needs every block to be detectable, and some software will work with, you know, it'll go into a sort of black hole until it comes to the next detector, and then the software says, oh, it's got there, so I better do something. And I think the Miniature Wonderland in Hamburg used the latter to an extent, is the impression I got from looking at their system. Indeed. Okay.
Noticed one of the questions was JMRI was a steep learning curve.
Yeah.
Are there any simpler alternatives? I mean, I would call iTrain simpler,
Yeah.
but different.
Yes, and I think the answer to that is true. I mean, Railroad and Co is used quite widely. I mean, I don't use it because it doesn't support the Merg C-bus that I use, but and it costs, you know, it's not that cheap. But my understanding from other people who've gone into this, and there's also some software called RockRail, which is another automation software, which does work with the Merg C-bus system. And what people have told me about those systems is that you'll get automation up, and possibly true of iTrain as well, is they're much easier to get automation up and running much more quickly. But you kind of have to be able to prepare to do it the way it does it. So with Railroad and Co, for example, if you want to do I'm getting some nods here from Dave. If you want to do all the nuances of UK signalling practice and do it properly, you may well struggle, because a lot of these softwares, well, they'll very well support the country of their author, which might be German or Netherlands for some of these cases. And of course, they will very much support US practice, because that's their biggest market for stuff that they're selling. So whereas with JMRI, you've got a bigger learning curve, but because it is so configurable and it has its own little scripting language, you can, if you're prepared to put the time and effort in, you can make it do anything, pretty much. So those are the pros and cons.
Point there, Pete. I would say James Hudson has influenced iTrain quite significantly.
Who was that, sorry?
James Hudson down at DCC Train Automation.
Okay, yeah.
James has, shall we, moved it away from continental signalling to include British signalling.
That's good to see. Yeah, it's good to know. Yeah, yeah. And I think, I mean, I did talk to them briefly about supporting the Merg C-bus system, and I think, you know, if they felt it was worth their while, they would at some stage, and that could happen. You never know. Right. So I look down to the next question. Right, from Ian Lancaster. At what point did you decide you need a booster? Right. Technically, a command station only produces the digital signal at 5 volts, and it's the booster that converts that to the full thing for the track. So you always need a booster of some sort, but many command stations come with a low current booster built in. So if you're thinking of the Merg one, for example, it's got 1 amp built in. I think the Sprog is probably similar. NCE, for example, the handsets on their own, the power cabs, have a low power, I can't remember, probably an amp or so, again, quite typical. And then, so it's when you need more than an amp,